Okay, yeah, my name's Abe Stanway. I'm a data engineer at Etsy, and I'm here today to talk about algorithms. This picture I actually took myself on a recent trip to India, and that little girl was crying because I had tried to explain to her how Nagios worked, which is a common reaction when you try to think about all of our monitoring tools, and that's a problem. The good news is I have a solution. I know, if I can move the next slide here. Come on, what is this technology? Whatever. I know how to fix monitoring once and for all. And it's a bold statement, but that's what we're here for. We're here to learn how to do things the right way, possibly. But I know I have a solution that I'm going to tell you at the next slide that is robust, effective, and super simple. And if we had it, our lives would all be much better. Ready for this? It's a real human being physically staring at a single metric 24/7. Okay, so picture the scene. You've got an army of monitoring technicians that you hire, and you sit them down and you say, it's your job to look at this metric and then alert a sleeping engineer, pick up the phone, call them when your metric is doing something that you don't think it's supposed to be doing. Boom, that's all we got, perfect monitoring. And that would work, right? I would feel really, really comfortable as an engineer knowing that that system had my back. Of course, we can't actually do that. You know, it'd be prohibitively expensive. It is of dubious ethical consequence, but it would work. And it would work because humans are still really, really good visual pattern matches for certain types of things. That comes with a big asterisk. We're not really good at pattern matching for really, really complicated, kind of intricate statistical applications like cancer detection or really kind of situations where it's not easy to see how there are patterns in the data. But for ops metrics and monitoring, I think you're hard-pressed to find something that you can't visually determine if it's normal or not. And if that is the case, then I don't know what kind of monitoring you're making. It wouldn't make sense if you couldn't watch it and see. So the question becomes, can we teach software to be as good as humans are at anomaly detection and monitoring? And that's what I'm going to explore in this talk. So let's get started. So some definitions. When I say anomalies, I mean not normal, quote unquote. And when I use this word normal, I mean it with zero connotations, no mathematical connotations whatsoever. Like I just mean it the way you and I would say normal. Like this is normal, this seems normal to me. And humans can tell what normal is just by looking at a time series. You can say, hey, does this look normal to you? Without meaning anything special by it, just using our intuition. And so we can use that to kind of make a job description for our hypothetical monitoring technician. And the scene is he or she comes in, fresh face, first day of work, ready to get started monitoring. And the manager says, okay, sit down, here's your metric. And he says this sentence: if a data point is not within reasonable bounds, more or less, of what usually happens, it's an anomaly and you should call me. And then they would hear that sentence, they'd say, okay, I can do that, sit down, and that's all you have to tell them. And then they'll immediately be able to look at the time series, zoom out maybe a little bit to get some more context, and know what normal means for that particular time series. The good news is that there are real statistics that describe what we mentally approximate when we do this, our intuitions. And we're going to dive into a couple of those. So here's an example of a time series. This is something that could presumably exist on any of your dashboards, describing a real process with real data. And in fact, this actually was taken from a real process with real data from my dashboards. So when I say what usually happens, now what I'm doing now is I'm breaking down the initial job description, right? So if a data point is not within reasonable bounds, more or less of what normally happens, it's an anomaly. So what usually happens, that's the mean we're talking about. We're talking about the average. If I asked you to just draw a line or just guess a data point that described the average, you'd be able to do it with a reasonable amount of accuracy, right? And the machine can do that too. That's pretty easy, right? You can kind of see the middle of this time series is where I would draw that line, and that is the actual mathematically calculated line of the mean. We approximate that in our heads. When I say more or less, we're talking about the standard deviation. Okay, this is a measure of how spread apart the data points are. So those two green lines indicate one standard deviation above the mean and one standard deviation below the mean. And that is more or less what the data is likely to be. When I say within reasonable bounds, here's where it gets a little bit more intuitive. The goal is to see something like what is an unreasonable value of this data point. And it's clearly not going to be just one standard deviation, because we see a lot of the time it goes above one standard deviation. It's not unreasonable for a data point to appear above one standard deviation. It's not really unreasonable for it to appear above 2, because we see it does that a couple times. But maybe 3 standard deviations, okay, maybe if it goes above or below 3 standard deviations of the moving average, then that would be an unreasonable value of this data point. So we'll stick with 3 sigma, right? And sigma that's the Greek term for standard deviation. I'm going to be using that word 3 sigma to refer to this whole process for the rest of the talk. So mathematically, what we've done is we have taken our initial sentence, our English human sentence, and converted it into mathematical terms that we can then program into the computer. So that is, a metric is anomalous if the absolute value of its latest data point, right? So if it's above or below, is over 3 standard deviations from the mean. Okay, so just to picture that one more time, a metric is anomalous. It's anomalous if the absolute value of its latest data point is over 3 standard deviations above and below the mean. And this is an important sentence, because it is essentially what it is this thing called statistical process control, which is a pretty old concept. It's older than all of us in this room, probably. It was pioneered in the 1920s by a guy named Walter Shewhart at Bell Telephone Company for the purposes of monitoring the quality of switching circuits. And it caught on, right? The idea is that you're mass producing all these things and you want to have a kind of QA. And so what you do is you give these things called control charts to the QA engineers who watch the assembly line. You pick a metric that's representative of the quality of the product that you want to measure. You give them a control chart that really all it has is the 3 sigma, top and bottom, and you say, when the data goes above and below this value, which is pre-calculated for you, then you know something's wrong with your process, then you should fix it. And that's statistical process control. But it has some constraints. It's grounded in what's called exchangeability. This is a statistical concept. Exchangeability means the past can be roughly equal to the future at any given time for any sample on your time series. Okay? So you should be able to take any random chunk of time, like a minute, at any time of day, and be able to superimpose it at any other time of day, and still have the same distribution, the same parameters, the same mean, and the same time series. It should be described by the same process at all times. It needs to be stationary. That means it can't go up and down with respect to the time of day, right? Because when you think of an assembly line, a telephone circuit or a car made at 9 a.m. should be the same as a car made at 9 p.m. It shouldn't matter. So if for a working process that's static, to do this kind of quality control, you need to have stationary time series. And importantly, it needs to be produced, the data, by independent random variables with well-defined expected values. This is a little bit of a more abstract concept, but when I mean independent random variables, I mean the data at any point should have 0 correlation to the data at another point. And it should be constrained by, it's random with respect to what it probably is going to be, which is going to be mean, right? And so when you get really genuinely independent and random variables, that means that they're more likely to revolve around the mean, right? And you get that kind of fuzziness around the process that we saw before, that you're familiar with. And this is useful because it allows for good statistical inference. It allows you to just quantify that fuzziness as Brownian motion, right? And disregard it for all purposes and just think of it as a line. And then once you have that, then you can start to think in terms of what is not that process. In other words, you need really good-looking time series for SPC and 3 sigma to work. One concise definition of a good-looking time series is the normal distribution. You've all seen this bell graph before, but this is really, really relevant because if you have data that can be described by a normal distribution, when you take the distribution of all the data points and it looks like that nice Gaussian bell curve, what you've probably got, chances are, is a exchangeable stationary series produced by independent random variables that you can then use 3 sigma statistical process control for. And the normal distribution is very cool because you can think of it in terms of the standard deviation, right? So for this one, we see that for a perfect normal distribution, I think it's like 68.2% of all the values are within 1 standard deviation. I forget the number for the third, but if you go all the way out to 3, you get 99.7% of your values fall within 3 sigma of the standard deviation, within 3 sigma. So that's a pretty big number, okay? That's going to be like all the time, right? And if it's not in that value, so like you see those red lines there, those indicate the standard deviations. There's 1, there's 2, and there's 3, and you can't even see the third one, but it's right there, right, on either side. And if it's in this little area there, which is that 0.3%, then on either side, then you're dealing with an anomaly. And so it's really, really, really unlikely to happen in there. So when you've got that scenario, when only 0.3% lie above, in absolute value terms, above 3 sigma, you get a really, really high signal-to-noise ratio, where signal indicates a fundamental state change, as opposed to a random, very, very improbable variation, okay? This is an important concept. A fundamental state change in the process means that the process is being described by a different probability distribution function, okay? Which is a parameter of the data. So what we can, I'm going to go into this in a second, but what we can do is define anomaly detection as the science of determining when probability distribution function shifts have occurred as early as possible. Okay, to illustrate that, here is, say we've got a process that has this distribution curve, okay, nice and normal, it's looking good, and then an anomaly happens, okay? All of a sudden, if we were to let it continue to run, the process would be described by this secondary curve here, okay? And so say your system's acting normally, and all of a sudden it breaks, and now it's described by this new curve. Well, if you look at here, it's probable that a lot of these values here are going to lie in what was the 3 sigma range of the old one, right? So you're going to get a lot more of them. So all of a sudden your alert's going to start like alerting you and saying this is different, this is different. And so it's not a very, very improbable chance that they just all happen to be happening with the same curve. It's actually a fundamentally different curve, right? With a different mean, right? mu1 and mu2 that describes by the curves. And so to illustrate this more, the kinds of processes that this works really well for are industrial processes like forging steel, drilling holes, sawing boards, right? So you can think of all these processes in terms of their distributions and their variations. Like for example, with drilling holes, which is the kind of classic example, every hole that is drilled, right, all day long, is not going to be the same size atomically speaking, right? But they're going to be around the same size. It's been designed to be a certain size within reason, right? And that the size of the hole, if that's your metric, is going to be measured by a certain distribution function. When you have a state change, right, like your drill bit snaps or something, there's still going to be data produced. There's still going to be holes maybe being made, but that data is going to be described by a fundamentally different distribution function. And so if you detect that, then you know that, okay, my drill bit snapped, I have to go fix it. So these are all processes with well-planned expected values that only suffer small random deviances working properly and massive deviances, quote unquote, when working improperly. Except these deviances aren't actually deviances, they're not errors. They're just described by different curves. Okay. So the bad news is that server infrastructures are not like assembly lines and traditional industrial processes. The systems that we build are active participants in their own design. Okay, they don't get designed beforehand with respect to a spec to hit metrics, right? Like in an assembly line when you're making cars, you design your car with a blueprint. You have, okay, I need a hole this size, and then let's execute on this model so we get holes that size, right? With us, we say, well, I need to serve a lot of users, I guess. Let's build something using my very abstract concepts of I/O and CPU usage and the cap theorem, right? Which are not really very, very solid. and build a system that I think is going to work and see what the metrics look like, and then if they're satisfactory, then I'll just leave it. Or if they're not, then I'll make it better until something does look good, right? And then that becomes normal. So the system actually informs you and iterates, and this is what continuous deployment's all about. And it's good. It's how we build systems on time. But it's bad if we want to monitor. I forget this still doesn't work. Seriously. And the reason why is because our processes don't have these well-defined expected values, right? We don't sit there and say, I want to build a system where it gets exactly 20% CPU usage before we've built anything at all, right? We may make that a goal, we may make that an SLA later on when we're optimizing, but not when we're building it. The processes that, the data that we do get are not produced for many metrics by genuinely independent random variables, right? A variable is not independent if it's really high at one point, it can be correlated to another high value at another point, right? And if we're talking about disk space growing over time, yeah, a really high, 100 gigabytes now is probably going to mean 100 gigabytes in a minute unless an action changes, right? And so they're correlated, which means you don't get these random fuzziness variances. And in the cases where you do get those variances, large standard deviations do not necessarily indicate poor quality, okay? You can have a server that's humming along at 1% for as long as you want. All of a sudden you're on Reddit, you get an influx of hundreds of thousands of users and it handles them, right? So it goes up maybe 50, 60%, but the system's still acting normally. There hasn't been a fundamental state change, and it's not really an anomaly. You don't necessarily need to know about it. And they also have seasonality, right? We have users, we have these dynamic elements to our system that makes the system itself not the same system from at 9 a.m. to 9 p.m. because of our users. And this has complex effects in the systems that we have. So what you get out of all these problems is you get really skewed distributions, right? Where if you see, you get less than that huge big number, 99.7% of your values will fall within the traditional 3 sigma, right? So here we've got a distribution. There's 1 sigma from the mean, 2, and 3, right? And this is where we would normally alert anything after this. But if you see there's kind of a non-trivial amount of data that falls after 3 sigma, right? That could actually be indicative of a normal process. So that means it's really it's really noisy, right? And so that's the big dirty secret of using these 3 sigma SPC-based algorithms, right? You get a lot of false positives, and you get a lot of noise, and you probably get a lot of false negatives as well. And the problem with getting these false negatives is if you're dealing with 250,000 metrics and a ever larger number growing of metrics, there's no way to retroactively find the false negatives short of combing it with human eyes, right, to iterate on your algorithms. Because if you knew how to programmatically find these anomalies, they wouldn't be false negatives in the first place. You would have detected them. So the only way to iterate on a massive scale is to go through everything that your algorithm doesn't think is anomalous, look at it, right, comparing against your intuition, which is the kind of golden scale here, and then try to get your computer to be closer to your intuition. So how do we combat this? I'm about to throw some ideas on you. I haven't implemented most of them, but let's hopefully it inspires everyone to kind of move forward. So the first thought is we could always use custom fit models to describe our processes, right? This has the advantage of it can be very intricate, and we have to realize that it's not necessarily non-normal distributions that are the problem, it's the errors from the model that are the problem. Okay, where an error means the deviance is that fuzziness, okay? As long as you've got a model where the errors are normal, then you can use 3 sigma to determine when you're getting errors that are not normal, right? So for SPC, the model we use is just the mean, right? And it's a very, very simplistic model. We can have some kind of linear regression to find what is normal. But when you have a series that maybe looks like this, you're going to get in trouble, right? So this is taken from a capacity plan exercise that we did a couple months ago at Etsy. These are page views, right? And so the task was, okay, like let's predict the number of page views we're going to get over the next year and a half or so, so that we can predict how many servers we'll need to buy. So the blue data is the actual historical data that I had, and then the green is the forecast. So to get this green, I had to build a model using a lot of parameters, using the fact that I knew that there's a yearly cycle, using the fact that I knew that this bump is kind of Christmas, and that is to be expected, using the fact that I can kind of see that we're growing anyway, and kind of take that all into account and make a kind of artisanal, handcrafted model, as you do at Etsy. But this is hard to do, even by hand, right? This is a process, and it's hard to get computers to make models. It's hard theoretically and hard computationally to get them to do this, to automatically make models. There is hope, though. It is possible to implement a class of machine learning algorithms that determine models just based on the distribution of their errors using what are called QQ plots. So what you basically do is you take, well, a QQ plot is a quantile plot, where you can basically compare the distributions of two functions, two series. And so you would say, okay, I have got the normal distribution. I'm going to compare that against what my model predicts for this data. And when it's a straight line across, right, when it is normal, when I have determined that the model I have made is now normal, then I'm just going to use that model, whatever it is. It's possible to do something like that. And then once you have that model for the data, then you can use it to determine the errors, right? And so then for every data point that comes in, you say, is this error within 3 standard deviations of what the kind of errors I normally see, right? An error is a statistical term. It's not bad, right? It's that random variance. It's the fuzziness that you see. That's the error from the ideal, which is the model. QQ plots are also cool because you can also theoretically use them to determine if the probability distribution function has changed, right? Because remember, they measure distributions against each other. So if you have your original distribution and you're always comparing it with new data coming in, remember, if we defined anomaly detection as the art of detecting when these functions have changed, right? Because the processes, they're described by, the data describe different processes. And so the reason this is hard to do in real time is because you want to know about an anomaly as soon as it happens, which means you're only going to have like 3 or 4 data points, and your system's broken at that point. And you really need a bigger sample size to determine what the new distribution is to compare it against the old one. So, and this is kind of, it doesn't really matter what your resolution on your data is. So it's hard to do. You could use a consensus model. You could say, okay, you know what? I'm not gonna sweat it. I'm gonna implement everything I get my hands on, read all the papers, throw them all at the algorithm, hope it shakes out in the end. So the model we get is we've got our data, our time series. We run the time series against our suite of algorithms, and then let them hold a vote, an election, and if the majority wins. If they all agree that it's anomalous, then we go ahead and alert. But the problem with this is that if all your models are inherently SPC based, if they're 3 sigma based, and you're kind of riffing on that theme, then this doesn't really get you anywhere because they're all going to succeed and fail simultaneously. And you're not really going to get that spread of checks if they're all kind of based in this core concept of 3 sigma. So we need a new core concept. You could use exponentially weighted moving averages to adapt faster to new distributions. This is generally a good idea because when you're talking about ops monitoring, historical data doesn't mean as much. Right? You don't need to know what your servers were doing 4 months ago in order for you to accurately determine what they're doing now. If you use weighted averages, you kind of discount the older data and count the newer data more. And so that can alleviate things. For the seasonality problem, you could possibly use Fourier transforms, right? So you can use a Fourier transform to detect the periodicity of your model and detect if it is seasonal at all, and then possibly use some kind of machine learning to automatically make a model for that. But even this problem is tough because seasonal metrics, you just can't find the average of them, and you can't throw them through the standard SPC based because the mean of a seasonal time series is not an informative parameter. It's like it goes through it, right? Just the average. You can have a binary series of 1 and 1,000, right? And it just cycles between those two, right? The average of those is going to be somewhere in the middle, right? And that's not actually going to describe anything. You could try to find second order anomalies, right? So you can maybe accept that your stuff is going to be really, really noisy and say, okay, fine, I'll use SPC. It's going to be really noisy, but at least I will have a record of how noisy any particular metric is, right? And so you say, okay, I've got this particular performance metric that is always annoying me, whatever, I'm going to learn it, and then I will have it alert me when it's triggering using the normal algorithms more than normal, or when it's not triggering as much as normal, right? And use that. That's a possibility. But it's all very hard to do in practice and to verify that it's working theoretically and in practice. So to move forward, we can do a couple things. We can either change what we expect out of monitoring and treat it as a way of building noisy situational awareness, not directives, right? Not alerts, which is not ideal, because like what we want, right? We want alerts, right? That is the expectation now. Our ideal systems are, we just worry about building the systems, worry about having our lives, and worry about sleeping at night, and let the systems themselves worry about telling us exactly when they're broken and how they're broken. That's what we want. But if we abandon that and just treat it as a way of building situational awareness, then there is a future for these algorithms. But if we don't want to do that, then we kind of have to change what we expect out of engineering, which is to say we need to have strict specifications with expected values of all our metrics and models to describe our systems, kind of like NASA would do, right? When they're going to the moon, they make a model of the trajectory of the shuttle they want to go, and they make a system that obeys that model, right? It's kind of like test-driven development for modeling, right? For metrics, which we certainly can't be expected to do, because we just want to just whip them out. We got users, we have businesses to run. This would be so expensive to do. Plus, no one dies if our systems go down, so it's like we can't really be bothered to do that. And so neither of these things are going to happen, right? We still want the alerts, and we're not really going to put in the time to make these specifications so we can have these really well-defined models. So that means the only thing that we can do is move forward to make these algorithms work, which is going to be really, really hard. So hopefully the ideas presented here, I've been thinking about this a lot, and hopefully the ideas presented here will illustrate the path forward, so we can all kind of pitch in and do this. But it's not going to be fun at all. Thank you.